everyone, and welcome back. Today we're going to continue our exploration of hypothesis testing and introduce a method that we can actually test more than two population parameters via a nice intuitive way without actually introducing any new mathematics to us. So let's actually just review a two population test that we actually already discussed, and then we're going to extend it to more than two populations. In particular, let's assume we're interested in testing that the population variances of two populations P1 and P2 are equal to each other. And let's assume that we're going to be working with the two-sided alternative that sigma 1 squared is not equal to sigma 2 squared. Keep in mind that we can use a point estimate for the quotient of variances because then we can use an F distribution provided that these two populations are normally distributed. So let's suppose that P1 and P2 are both normally distributed. So if that is the case, then our F test statistic is going to be equal to the quotient of our sample variances S1 and S2, and we can choose these in such a way such that the quotient of them is always strictly greater than or equal to 1. So in some sense we don't need this two-sided alternative, and we can instead work with the sigma 1 squared is strictly greater than sigma 2 squared, i.e. we're going to be using a one-tailed test for this particular hypothesis because we have at least this degree of freedom in terms of our choice. So in this case, what are we actually testing for? So if we have a test statistic that is close to 1, that means we have evidence to believe that these populations are homoscedastic to one another. And if the quotient is significantly greater than 1, that means we have evidence to believe that these populations are heteroscedastic to one another, right? So some people will also call this a test for homoscedasticity. Homoscedasticity. Okay, so let's actually introduce a couple numbers to sort of see how we would actually go about how to test that. So example, suppose we have one sample collected from a population of size 26, and let's assume that its sample standard deviation was equal to 5.6. And let's assume that we gather a sample from a second population that's also normally distributed of size 13, and let's assume that that sample standard deviation was equal to 7.1. So from both of these sample test statistics, we can get our F test statistic for our test for homoscedasticity to be equal to the larger variance, 7.1 squared, divided by 5.6 squared, the smaller variance, which one can find to be approximately equal to 8.0656. So clearly that is bigger than 1, but is it sufficiently bigger than 1 statistically? So we need to compare this, for example, to a critical value or some alpha value once we calculate that p-value. So we need a distribution that this f-test statistic is associated to. So remember that this is going to be associated to an F distribution that has 12 degrees of freedom on the top because that is our top variance, and this is going to be our bottom variance. That means that's going to be 25. So that's going to be associated to an F1225 distribution. So once we are able to decide which distribution we have that this F-test statistic is associated to, and we have the test statistic that we've actually calculated from our samples, that means we can go to our F1225 distribution, which looks sort of like that, and then we can find our F-test statistic on this, look in the direction of our alternative hypothesis, which is a right-tailed test, and we can find that area there, which we know to be our p-value. So using some software, you should be able to find that that's going to be 6.47 approximately times 10 to the minus 6, which one can say is approximately equal to 0.12345 right? So some people usually use 5% as a cutoff value for your p-value to be sufficiently small, but regardless of the alpha value you choose, this is probably going to be smaller than one alpha value that you choose. So since we have a low p-value, that means we have evidence to believe that our null hypothesis is wrong. Therefore, we have a conclusion of rejecting the null hypothesis that the variances are equal to one another, and that means what in terms of words? That means we have evidence to believe that P1 and P2 are. So if we're rejecting the claim that the variances are equal, that means we have evidence to believe that these populations are heteroscedastic. And that's how we do an F-test for the equality of two population variances. Now let us see if we can extend this up to a finite number of populations. So now let us assume that we have k populations that we want to test the equality of variance on. In particular, we want to test that sigma 1 squared, sigma 2 squared, sigma 3 squared, all the way down to sigma k squared are all equal to one another, with the two-sided alternative that at least one of these two populations are heteroscedastic to one another. At least we have evidence to believe that they are. So, how can I go about testing this? So, without actually introducing any new, I guess you could say, mathematical tricks, what we can do is do what we call pairwise comparisons for all of these k population variances. So, what we can do is we can re-represent this grand null hypothesis into some sub-sample null hypotheses. In particular, we can test, for example, sigma 1 squared is equal to sigma 2 squared with an f-test. We could also test sigma 1 squared is equal to sigma 3 squared with a f-test. We could also test, for example, sigma 2 squared is equal to sigma 3 squared with an f-test. And we can continue this little pattern all the way down to, for example, sigma 1 squared is equal to sigma k squared. Sigma 2 squared is equal to sigma k squared, and what I'm doing is I'm, in a sense, creating a matrix here, all the way down to the last null hypothesis that sigma k minus 1 squared is equal to sigma k squared. So how many different null hypotheses do I have here? So notice that I have one in that last row, so let's actually write this out. So the number of pairwise comparisons is going to be equal to, so we have 1 in that last row, we're going to have 2 in that penultimate row. In particular, we're going to be testing, for example, k minus 1 squared to, say, k minus 2 squared, and k minus 1 squared to k minus 3 squared. So that's going to be 2, and that's going to go all the way out to how many parameters are we comparing in that particular thing. So notice that we're not comparing 1 with 1, we're not comparing 2 with 2, and we're not comparing 3 with 3. We're starting with 2, 3, 4, so we can sort of index that by the second population, so 2, 3, down to k. So that means there's going to be k minus 1 different population pairwise comparison test in that first row. So we have the sum of integers from 1 all the way up to k minus 1, and at least from pre-calculus you should know that that actually can be represented as k times k minus 1 all divided by 2. And if you're familiar with combinations, that's actually equal to ck2, which is just going to be equal to k factorial 2 factorial times k minus 2 factorial different ways. So that is how many pairwise comparison tests that we would have to execute for that particular grand null hypothesis in general. So let's actually look at a particular scenario, and let's actually work through some numerics on how we can actually go about this. So let's assume that we have 4 population variances that we want to test the equality of. So sigma 1 squared equals sigma 2 squared equals sigma 3 squared is equal to sigma 4 squared, with the two-sided alternative that they are not all equal. That means at least one of these two pairs are not or are sufficiently different from one another. So the first thing that we need to do is figure out how many different pairwise comparison tests one would have to go about doing. So notice that k is equal to 4. That means the number of tests, so the number of pairwise comparison tests, is going to be equal to 4 choose 2, which is going to be 4 times 4 minus 1 divided by 2, which is 4 times 3, which is 12 divided by 2, which is going to be equal to 6. So that's how many pairwise comparison tests that we need to execute here. Once we have the number of tests decided, now we need to gather samples from each of these 4 populations for which we're interested in testing the homosedasticity of. And let's also assume that each of these populations are normally distributed. You could of course do a test on the appropriateness of an f-test, but let's at least assume in this discussion that they are all normally distributed and an f-test is appropriate. So let's assume that we have the following test statistics from each of the 4 samples that we gather from those populations. So let's assume that S1 is given by 21, sample standard deviation of 5.1, S2 given to be 13 for n, and sample standard deviation of 4.3. Sample 3, let's assume that that sample size is 32, sample standard deviation of 6.2. And sample 4, let's assume that that's a sample size of 25, with a sample standard deviation of 5.4. So what we can do is actually construct what we call an Fstat matrix to sort of summarize all of our F-test statistics. So let's actually just go ahead and jump to what that is actually going to look like. So this is what we refer to as an F-test statistic. So an Fstat matrix. So the Fstat matrix for this is going to be equal to a 4x4 matrix. So we're going to have a 4x4 matrix here. So what we're looking at here is we're looking at, for example, sample 1, 2, 3, 4 versus sample 1, 2, 3, and 4. So we do the F-test statistic, for example, for 1 versus 1, but we already know that those are going to be equal to 1s. Because if we divide a variance by itself, then that's just going to be equal to 1. So 1 with 2, so we're going to be comparing those two standard deviations. So we're going to do 5.1 squared divided by 4.3 squared, and that's going to give us some number, and that's going to come out to approximately 4.1. And then we're going to do the same for 1 and 3. So we're going to do 6.2 squared divided by 5.1 squared. So that's going to come out to 1.48 approximately. And then that's going to continue on through all of our other different pairwise comparison tests. So those are all of our F-test statistics. And then from here, we can calculate what we call a p-value matrix. So a p-value matrix. Now the p-value matrix might be a little bit more technical to calculate because notice that all of our samples are a little bit different. So that means the p-values are all going to be associated to different F distributions, right? But if you know how to do it for one, you should be able to do it for all. So again, let's calculate our p-value matrix, which is going to be something along this form. So let's put diagonal entries of 1 down the diagonal. And also notice that I'm not actually doing the lower triangle of the F-test statistic matrix nor the p-value because we're actually looking at a one-tailed test here. So no need to do the lower diagonal. But at least from this perspective, it is at least symmetric from the conclusatory perspective, right? So what would the p-values be for those associated F distributions? One should be able to find that that's going to be 0.24, 0.18, 0.40, 0.09, 0.21, and 0.24. Now, you don't need to necessarily choose the same alpha value for every single one of these pairwise comparison tests, but usually it's common practice that you actually do keep your alphas consistent here unless you have some really good reason to do so. That is, you know something about some populations that you don't know about some others, right? So notice that for all of these p-values, right, notice that our smallest p-value is here to be 0.09, and the largest p-value is going to be 0.40. So let's actually summarize what we're looking at here. So we need our alpha to be, say, greater than or equal to 0.41 to reject or fail to reject the null hypothesis, right? So fail to reject the null hypothesis. Actually, no, that's rejection, right? So that's rejection. So reject the null hypothesis. And why is that the case? Well, if we were to choose 0.41, all of our p-values are below our alpha value. That means we have evidence to believe that they are significant different from each other for all of them, right? Because it has to satisfy for all, because if one pair doesn't work, then the entire null hypothesis is invalidated. So we need alpha to be greater than or equal to 0.41 to reject the null hypothesis, and we need alpha to be less than or equal to 0.08 to fail to reject the null hypothesis. Now, this alpha value to fail to reject the null hypothesis isn't too small. For example, most people usually choose alpha to be equal to 0.05 anyway, so let's just pretend that that is sufficient for our particular hypothesis test. So if we choose that particular alpha value, that means we will be failing to reject the null hypothesis because all of our p-values are greater than that alpha value. That means we have evidence to believe what? So if this test is actually appropriate, i.e. normality test is satisfied, that means we have evidence to believe that P1, P2, P3, and P4 are what? So again, we're failing to reject the null hypothesis. That means we have evidence to believe that they are homoscedastic to one another. So they are homoscedastic, or we believe that they are. We have evidence to believe that they are homoscedastic to one another. Now, if you were to choose an alpha value between 0.08 and 0.41, I'll let you sort of contemplate on how we would actually go about interpreting that particular result. Now, one may be thinking, well, if I can actually do pairwise comparison tests for multiple populations, what's the reasoning behind introducing other methods? Well, keep in mind, every time you do a hypothesis test, you have the possibility of making a type 1 or a type 2. Therefore, since we have k choose 2 different types of pairwise comparison tests to conduct, then that means each time you do that, and of course keep in mind, as k gets big, the number of tests that you have to do grows substantially big in terms, in particular, quadratically, right? So it quadratically increases the number of type 2 errors that you could possibly make in that particular procedure. So if you could possibly test the equality or non-equality of all of those variances or means or medians or whatever parameter you're working with at once without doing individual tests, then that of course is so much more better because the possibility of making a type 1 or type 2 error is only 1 instead of k choose 2. So with that little bit of advice here, let's actually do just another example on pairwise comparison tests, but instead of looking at the variances, let's look at the means. So let's assume we're interested in testing that mu1 equals mu2 is equal to mu3, and we'll use the alternative that either mu1 does not equal to mu2, or mu2 does not equal to mu3, or mu1 does not equal to mu3. That's equivalent to writing that mu_i does not equal to mu_j for at least one pair ij, right? At least one pair ij. So that's actually the same exact thing, just in case you're curious. So how many pairwise comparison tests do we need to conduct here? So the number of pairwise comparison tests in this case is going to be equal to 3 times 3 minus 1 divided by 2, which is going to be equal to 3. So we just need to do 1 versus 2, 2 versus 3, and 1 versus 3, and then we are done. So let's also assume that each of these populations, 1, 2, and 3, are all normally distributed so that a t-test will be appropriate in testing the equality of each of these means. So let's go ahead and grab some samples from these populations. So let's assume that S1 is of size 31, a sample mean of 5.8, and a sample standard deviation of 3.6. And let's actually just state out the statistics for these other two samples for which you were to draw from those populations. So keep in mind, we have these point estimates for x bars, right? So x bar is equal to 7.4, sample size of 38, sample standard deviation of 3.8. And we want to see if those point estimates are significantly different from each other to imply that the difference between the parameters for which they're trying to estimate are significantly different for each other. So the very first thing that we need to test is whether we have evidence to believe that the variances amongst each of these are significantly different from each other. So what we need to do is do an f-test for the variances because we need to see, can we use a pooled variance t-test or Welch's unpooled variance t-test for each of these pairwise comparison tests. So for homoscedasticity, one can find that the p-value matrix is going to be equal to, and I also highly recommend looking at p-value matrices, not test statistics, and critical value matrices, because you can make up your own mind whether these p-values are sufficiently large or small. But one can show that this is going to be equal to 0.01, 0.38, and 0.44. So if we choose, for example, alpha is equal to 0.05, then we reject the equality of variances for pair 1 versus 2. Remember, this is 1, 2, 3, and 1, 2, and 3. So we have evidence to believe that populations 1 and 2 are not homoscedastic to each other, and we have evidence to believe that populations 1, 3, and 2, 3 are significantly different from each other. Okay, so let's actually write that down in words. So we have evidence to believe that P1, P2 are heteroscedastic, and we have that P1, P3 and P2, P3 are homoscedastic. to one another. So for heteroscedastic populations, or at least we believe that they are heteroscedastic, we need to use an unpooled variance t-test. And for the homoscedastic case, we can use a pooled variance t-test. And now, since we know which test we can use, now we can go ahead and use them. So let's go ahead and start with the unpooled variance t-test P1, P2 test. So what is the standard error associated to the differences in sample means? All right, so we're going to be looking at P1 and P2 here. So the standard error for x bar d for an unpooled variance t-test, remember, is just going to be equal to s1 squared divided by n1 plus s2 squared divided by n2. So using those statistics that I mentioned earlier, one can find that that's going to be approximately 0.87. The only complicated part about the unpooled variance t-test is the degrees of freedom, where we need to use the Welch-Sadet rate approximation for the degrees of freedom, which remember is just going to be equal to the standard error of x bar d to the power of 4 divided by s1 to the power of 4 n1 squared times v1 plus s2 squared to s2 to the power of 4 divided by n2 squared v2. And once you actually work through that, that's going to be approximately equal to 67.65. Once you have your degrees of freedom and your standard error, the rest should be very, very easy. And keep in mind, we're going to be approximating this via the p-value perspective. So we need to calculate our point estimate for x bar d. So that's going to be equal to the positive difference between the sample means of populations 1 and 2 that we calculated. So that's going to be approximately equal to 2.7. And then from x bar d, we can calculate our test statistic. So our t-test statistic for P1 and P2, remember, is just going to be equal to x bar d minus the claimed value of the difference, which is, in this case, going to be equal to 0, because we're trying to test if there's a significant difference between them, divided by the standard error of x bar d for our particular sample, which was 0.7, and that's going to come out to a friendly 3.07. So from this test statistic, we already know our degrees of freedom for the t-distribution that we're working with, so we should be able to calculate our two-sided p-value to be approximately 0.0030. We'll come back and interpret this in just a moment. Now let's look at 1,3 and 2,3 in terms of its test statistics and p-values. So for P1 and P3, remember that we're using a pooled variance t-test for 1,3 and 2,3. So remember that the pooled variance for two samples is going to be V1 S1 squared plus V2 S2 squared divided by V1 plus V2. And some people will also say that V is just equal to V1 plus V2. Now, since I'm working with populations 1 and 3, you may want to change your subscripts here just to avoid any ambiguity here. So this is technically V1 and V3. So let's just actually just make that quick change here. So once we have our pooled variance, we can find the pooled standard deviation by taking the square root of it. And then from it, we can find our standard deviation for x bar d between 1 and 3, which is going to be equal to the pooled standard deviation and 1 over n1 plus 1 over n3, since we're working with 3, not 2. And that's going to come out to approximately 0.8983. Once you have your pool, our standard error, and you have our degrees of freedom, remember, which is V1 plus V3, then we can calculate our test statistic. So again, our test statistic, t-stat, is going to be the same exact structure as before. The only difference is that our standard error for x bar d is a little bit different, and our x bar d is looking at a different difference of sample means, right? So once we calculate our test statistic, we can find that the associated p-value for the degrees of freedom t-distribution that we calculated before is approximately 0.8245, which is substantially large. And doing a similar fashion for P2 and P3, which is also going to be a pooled variance distribution, pooled variance t-test, you can find that the p-value between them is going to be approximately 0.9064. Now that we have all of our p-values for our three paired difference pairwise comparison test, let's summarize those results in a p-value matrix. So our p-value matrix is going to be equal to a 3x3 matrix, where we only need to look at the upper side of this, right? So 1, 1, and 1. So we have 0.0030, we have 0.8245, and 0.9064. And let's just label this. So 1, 2, 3, 1, 2, and 3. And notice that we have that these are very, very large, right? So what are we trying to say there? So these are very, very different from that one. So let's assume that we're working with an alpha value of 0.05 for the entire main hypothesis test that we're working under. That's why you shouldn't be looking at critical value and test statistic matrices for comparisons, because the alpha value may change and you don't want to sort of do that because that could actually be biased. So if we look at an alpha value of 0.05, notice that this value right here is actually going to lead us to reject, right? Because with that p-value, we're going to be rejecting that p1 is homoscedastic to p2. That's what we're rejecting there. Nonetheless, since we're rejecting that equality of variances, that means we're going to be rejecting, equality of means. That means we're going to be rejecting, so what we're rejecting here is going to be that mu1 is equal to mu2, which means we're going to be rejecting, as a result, mu1 is equal to mu2 is equal to mu3, because we found one pair that is significantly far from each other, right? So let's actually look at this from a numerical perspective to sort of see what's going on there. So remember what our sample means were. We had 3.6, 3.8, and 3.9 for our sample means, which are point estimates for the population means. So 3.6 was for population 1, 3.8 was for population 3, and 3.9 was for population 2. So we have evidence to believe that population 1 and population 2 are significantly different from each other. And obviously those are the most distant sample means, right? So that actually makes some sense, right? Because if we reject that 1 and 3 are substantially different, you should also be getting, if you haven't changed your alpha value, that 1 and 2 are substantially different, provided that they're working on the same exact test, of course, right? But you should actually see something very, very interesting here, because from at least our test, statistic, and p-value approach, we have evidence to believe that 1 and 3 are at least statistically close. From our hypothesis test, we also have that p3 and p2 are also statistically close, but from our hypothesis test, we have that 1 and 3 are statistically far from each other, right? So you should see that hypothesis tests are not transitive. And what do I mean by hypothesis tests are not transitive? So that means if you have that 1 is close to 2 and 2 is close to 3, that does not necessarily imply that 1 is close to 3. Right? Which some structures, such as less than or equal to, for example, if x is less than y and y is less than z, then x is less than z. Yes, that's perfectly transitive, but hypothesis test conclusions are not. So you definitely need to be careful of that, because that's a common misconception in pairwise comparison test. But pairwise comparison test does give you some way of testing the equality of several different parameters, with the downside that you could be making a type 1 or a type 2 error for every single pairwise comparison test that you're actually conducting here. But we are going to be looking in some more sophisticated methods that aren't pairwise comparison tests, for example, that will test the equality of means, variances, and several other parameters. So until then, I hope you take care. See you then.